Okay, so in our process now of solving systems of linear equations, we have a lot of stuff set up. We have a target, something to aim for, and that's reduced row echelon form. We want to take a system of equations and get into reduced row echelon form because of all the wonderful things about that form. In particular, you can always solve for your pivot variables in terms of your free variables, and that will allow you to always write down the complete set of solutions. And we have a process by which we're allowed to try to get there. Namely, we're allowed to do elementary row operations. Elementary row operations always preserve solutions. So we have steps that we're allowed to take. We have a goal that we would like to achieve. And the next natural question is, strategically speaking, how do we get there? How do we, what's the most efficient and effective, a reliable and reasonably efficient means of actually accomplishing that goal? And the answer that we're going to talk about is Gauss-Jordan elimination. Roughly speaking, the idea is to fix the columns one at a time, left to right. So, for example, now this next example is deliberately set up to be convenient. Everything works out nicely. So, we'll start with the left column, left to right. Okay. So, what is it about this column that needs fixing? What is it we don't like about this column? Well, you look at the first entry and you think, well, maybe that's the first pivot, so that's not really a problem. But if that is, in fact, a pivot, then that means that these numbers have got to go. One of the requirements for reduced echelon form is that everything else in a pivot column, other than the pivot itself, has to be all zeros. So the way we make those numbers zeros, by way of elementary row operations, is this little trick here. So that elementary row operation, we'll look at just the second row for the moment. That elementary row operation, you do the appropriate arithmetic, and that gives you these numbers. And as required and desired, we have 0 there. Okay, now where did this row operation come from? What's the trick? Well, the big idea, of course, is we see that we have this -3, and we want to get rid of it. And we realize that that is something I can get rid of by adding a multiple of +1. And with that in mind, the fact that this is a -3, that motivates adding 3 times the first row to the second row. That gives us this 0. Okay. Now, of course, when you do row operations, you have to go all the way across. So even though turning that, as it were, into that was our only goal, you've got to take 3 times that entire row. 3 times that entire row plus that entire row. You have to follow the formula to get this entire row. Right? You're not allowed to do row operations just, one column at a time or something like that. Okay. All right. So with the same idea in mind, you can kill that -4 with this row operation here. Again, the -4 motivates that 4. Okay. And you'll notice as a result of these 2 row operations, which I've done in a single step, that column is now what I'm going to call fixed. So in other words, it looks like this. We've made some progress toward achieving reduced row echelon form. Okay, so next we ask, what's wrong with that column? What is it we don't like about this column? Keeping in mind, moving from left to right. So the first column's okay. Now we go on to the second one. Okay. So what is it we don't like about this second column? Well, is there a pivot in that column, we ask? Any chance that this might be a pivot? Well, no, of course not. Can't be the first non-zero entry in that row because we already have a non-zero entry in that row. So, no, that can't be a pivot. Well, gosh, what about this? Maybe there should be a pivot there. No obvious reasons why we couldn't, so, well, let's do it. So, I can make this a pivot Different things you could try to do. There's a temptation to maybe add a multiple of one row into this row to make that happen, but keep in mind, if you in some sense use if you use this to edit that row, then keeping in mind you have to go all the way across, then that means that this is going to do something corresponding to there, and you're going to mess up your nicely arranged zero. So let's not do it that way. A nice way to fix a position where you think there might be a pivot is to, as we have in this instruction, just divide that entire row by whatever is necessary to do that. So this being a 2, we divide by 2, and that gives us that row. And now this very well might be a pivot. Of course, now if it is a pivot, then we need to get zeros elsewhere in that column. That means we need to kill those. That motivates these two row operations, which, as you see, do give us the zeros where we want them. Okay. All right, so we fixed the first column. We fixed the second column. Now, again, moving left to right, let's go on to the third column. Now, this is nicely already got a 1 in the position where we think there might be a pivot, so we just have to kill those. We do that with these row operations, and we get zeros in those positions. So all together, we have pivots there, there, and there. We have the required increasing number of leading zeros, 0, 1, and 2. Everything in every pivot column is all zeros, and we have reduced row echelon form. Okay, so broad strokes. This is the strategy. This is Gauss-Jordan elimination: is to fix the columns one at a time, moving left to right, using row operations as necessary. Okay. Now, it won't always work out exactly this way. Sometimes there are little issues that come up. So here's an example. You'll notice now in this example the first and second columns are already fixed. And then we move on to this third column, and awkwardly, where I feel like maybe there sort of ought to be a pivot in that third position, well, it's a 0. I can't divide through by 0. That's not allowed in any sense. And anything that I might do, so for example, I can't switch these two rows because there's a 0 in that bottom row as well. Tempting to say, again, maybe you take a multiple of this row and add it into that row. But again, that'll mess up the zeros that I've already arranged there. So can't seem to get a pivot into that column. And the thing is, that's not bad news. It's not a problem. We do not have to get a pivot into every column. There is no requirement that there be a pivot in every column, or that we, pivots are defined as the first non-zero entry in a row, right? So the reality is, in this case, there simply is no pivot in this column. This column is fine. There is nothing about this column that's inconsistent with reduced row echelon form. So we leave it and move on to the next column. Okay, alrighty. Now what about this scenario here? Well, temptation is to want to try to get this to be a pivot. Can't divide through by 0. Right? So again, what do you do? In this situation, you could switch these two rows, and then you'd have something you could divide by. So you could switch and then divide that the new top row by 5. Of course, that would lead to fractions. So the cleverer move is to switch these two in this case. And then the new top row, when you divide by 3, would be all integers. You get to avoid fractions, at least for the moment. And that's a nice thing to do, keep your life simpler, if at all possible. Okay. So, in this situation, again, you want to put a pivot there. The temptation, the sort of the brute force thing to try would be just to divide through by 5, but clever move. Notice there's already a 1 here. You could just switch these two rows, and then you don't have to introduce, again, fractions unnecessarily. Okay. And here's one other little clever move. There's a endless supply of clever moves that you can do that will either avoid fractions or make the arithmetic simpler, and so you can keep on the lookout for these kinds of things. In this case, in order to get a pivot into the top left position, don't want to divide by 4. That would create fractions. Ditto if I were to switch and get any of these other rows into the top position. Dividing through by the leading term would introduce fractions. So in this case, I do this little move, just to take row 1 minus row 3, and that gives me a 1 in the top left position as desired. And then off you go into the rest of it. You got to kill these, etc. Okay. All right. So that's the short tutorial on Gauss-Jordan elimination. Now, one thing you want to watch out for is combining row operations. It's not rare to try to combine row operations into a single step. So, for example, in this row reduction I did here, I did this several times. Here, in this one step, I actually did 2 separate row operations. Right? That saves a certain amount of pencil lead, saves a certain amount of paper, and time, if nothing else. So it's tempting and convenient. You just have to be aware that it can be very problematic. So you take the ideas of the combinations of row operations we just looked at. You see here I have a little formula for what the second row is supposed to turn into, and then in the next step I have a formula for what my first row is supposed to turn into. And there's a temptation to, as on a few pages back, combine those into a single step. And that leads to the following arithmetic. You do these formulas for these rows, and notice you get something that is not the same as what we got previously. So it looked like we combined these 2 row operations. Well, it should be like this. It looks like we combined those 2 operations into a single step, but that's not what happened. So it's awkward. It certainly looks that way. But here's the mistake. Here's the problem. Looking back up here in the original reduction, the row 2 referred to in the second step here, well, that's of course per the rules referring to the second row in the previous matrix, right? But when I air quotes combine them into a single step, seemingly that same 2, well, that then is referring to a different row. So that and and that, these are not the same, right? So this thing here, cosmetically, at a glance, appears to be a combination of 2 row operations, but it's not. That's not anything. It's not a row operation. It's not a combination of row operations. It's junk. So this is something you have to be very, very careful about, and make sure that if you do combine if you write something down that at least at a glance appears to be a combination of row operations, you have to make sure that this actually can be achieved as a sequence of actual row operations. In this case, by the way, not only did we get a different result from that, In fact, these are not even equivalent. If you row reduce, right, this one's already in reduced echelon form. This, if you row reduce, gives you that, and these are not equivalent. They're different reduced echelon forms, and therefore they are not equivalent. Okay, so dangerous little problem, something to be careful about. So that being said, it is very convenient in some cases to combine row operations. I am not going to give a complete listing of all different ways that you can guarantee that your row operation or your combination of row operations, seeming combination of row operations, will be an actual combination of row operations. I'm going to show you one example and suggest how you can make the determination yourself. So here's the example. And that is, if you leave one row fixed, pick one row, don't change it as part of your step. And if, furthermore, you use only that row to adjust other rows, then you'll be okay. So, for example, let's look at this step here. Now, this is not a row operation, right? That is not a row operation. That, at a glance, would appear to be a combination of two row operations. But is it? Well, first of all, let's see how this is consistent with our rule. Leave one row fixed. Notice that I have, right? Row 1 didn't change. All right, next. Use only that row to adjust other rows. So specifically then, you'll notice that I've used only row 1 to adjust rows 2 and 3. Okay. Then no problem. Okay. And it's not hard to persuade yourself why this is going to work. You can see that because I've left that one row fixed, if I were to spread this out and break this up into an actual sequence of actual legal row operations, the result of doing this one would have row 1 still being exactly row 1, because row 1 didn't change in any of this, right? And so this row 1 reference in the second step that I would be taking then is, I mean, it may be referring to the row 1 from a changed matrix, but it's a row 1 which is in fact the same as the original row 1. And so there's no confusion, there's no inadvertent reference to the wrong row. Okay, so this is safe per this example. Okay, now there's variations on this. For example, this step that I've done here. This is actually a combination of 5 row operations. And this can be written as, I mean, you can actually go through and figure out, well, what are those actual 5 operations. I think this is a lovely exercise, and I want to encourage everyone to do this. Look at this step here that turns that matrix into that matrix, and explicitly write out the sequence of 5 separate row operations that would achieve this. And I think you can persuade yourself that, well, I mean, clearly there's I'm adding a multiple of one row to another, and then I'm doing that again. But then there's also a multiplication by a scalar, and a multiplication by a scalar, and then a multiplication by a scalar. So those are the 5. Now you got to be careful, because depending on whether you do the multiplication by a scalar first and then add a multiple of that row to others, then the coefficients are going to be different. So this is not a trivial question, right? Nevertheless, roughly speaking, the point here is that because all I've done to this row is multiply it by a scalar, if I need to add a multiple of it to something else, well, whether I have or have not already done this scaling, all that will do is affect what that constant should be. Maybe that constant will have to be different in order to get me what I actually want. But certainly it's something that can be So that'd be a nice exercise.